Good morning, everyone, and thank you for being here. We'll give folks about 30 more seconds to continue joining. We will kick things off in just a second. Thank you again for being with us today. All right, good morning, everyone, and welcome to NGA's Energy Innovation Webinar Series. As always, I'm thrilled to see so many folks joining and interested in this series. On behalf of all of NGA, we are delighted to have you join us. NGA members are at the forefront of our energy future. They are committed to supporting and achieving the ambitious climate and environmental goals that have been set across our region. From research and investments in emerging energy fuels and technologies to adopting new strategies to support efficiency and emissions reductions, NGA members are leaders regionally and nationally. This series reflects NGA's dedication to supporting our members as they embrace innovative solutions that not only address today's energy challenges, but also pave the way for a resilient, sustainable future. I would be remiss if I did not take the opportunity to plug that this series is a prelude to our inaugural Energy Innovation Summit taking place September 25th and 26th in Springfield, Massachusetts. We are developing a really exciting agenda for that summit, and we're going to have some announcements on that in the very near future that I look forward to sharing with you all. If you are interested in being involved in that summit or want to learn more, please check out our website or reach out after the webinar. I would love to hear from you. Now, as we begin, if you have questions, please use the chat function. I'll be keeping an eye on that throughout the conversation, and I'll try and interject where appropriate so that we can have a nice conversation throughout this webinar. And with that, it is my pleasure to introduce GTI Energy's Paul Glanville. Today, Paul is going to give us an introduction to the fundamentals of hydrogen and dive into Hydrogen 101 from the perspective of utility customers. Paul, thank you. The floor is yours.
Thank you. Looking forward to sharing some insights here. I'm going to go for a screen share, and we're going to get rolling. Thank you, everybody, for spending some time with us today here. As was just mentioned, I'd like to cover kind of burning questions, pardon the pun, for utility customers around the topic of hydrogen. My name is Paul Glanville. I've been with GTI Energy for about 16 years now. I oversee what we call our Heat and Power division, which is our research concerning buildings and industrial customers. And for that reason, I'm going to focus on that customer set. And just to kind of say that the topic of hydrogen, particularly as Hydrogen 101, is a big topic, and we are happy to engage further on this as your interests expand here. So let's dive right in. First, a quick introduction to GTI Energy for those who aren't aware or know us well. We're an industry nonprofit based in the Chicago area. We do have remote offices and laboratories throughout the U.S. And we've had a long-standing relationship with the natural gas industry, both midstream and for utilities as well. As a nonprofit, our primary function is collaboration. And what we look to do is work with our government and utility partners to de-risk and advance technologies that support the gas industry and the energy industry more broadly. And one way we do that is on the right-hand side here, are through industry collaboratives, ways that we work with utilities as a group and also other folks in the industry space as well. So please feel free. I believe my contact information should be provided. If not, it'll be at the end of the slide. If you're curious to learn more about us and how we work with industry, don't hesitate to contact us. So let's first start with why are we talking about hydrogen? So this is a chart here that shows the natural gas and electricity energy use for residential customers in Illinois, where I'm based at a state level. Natural gas on an energy basis is shown in blue, and electricity is shown in red. The main thing to highlight here, of course, there's some seasonality, as you would expect, between winter and summer, alternating peaks for both grids. But there's a significant difference in the energy delivered to Illinois residential customers from the gas grid relative to the electricity grid. And one challenge that we have, of course, broadly, not just in Illinois, is how do we decarbonize? How do we reduce the environmental impact while retaining the affordability and reliability of the gas grid with this challenge in mind? And where are there opportunities to have these grids support one another? And this is a big topic because the gas infrastructure is very large. I think as many folks appreciate, in North America, it spans more than 5 million kilometers. It serves more than 85 million buildings and facilities, which is quite a bit. The gas grid also delivers at about 600 gigawatts of energy. To put that number into perspective, the all-time peak of the California grid is about on the order of 50 gigawatts. So you can get a sense of the scale of energy delivered by the gas grid at its peak. And what it is really a form of storage. And that number, 1.3 petawatt hours, is a gigantic number. It's a form of energy storage that far surpasses what we are able to store energy in terms of pumped hydro, in terms of batteries and others. So it's a significant storage there. However, of course, it results, the use of that gas grid through those buildings results in more than 1,000 million metric tons of CO2 per year for heating processes. So that's a significant area for us to attack. So our premise is that we believe that the gas grid can play a constructive role in reducing the emissions and the environmental impact of the energy system broadly. And let's talk about how hydrogen can fit into that. So this diagram here shows it's a simplified diagram of what the energy system looks like today. You can see multiple forms of primary energy on the left-hand side, everything ranging from traditional fossil fuels to nuclear energy and biomass and solar and other renewables. Those energy sources can be converted or transported as is. The primary conversion, of course, is towards electricity, where most of those energy sources are used to create power for the power grid. How those energies are distributed or moved through the infrastructures can vary, and how they're stored as well can vary. And they're ultimately serving what we call end use, or buildings, transportation, and industrial. So all the customers that are served by the utilities today. Now, how would this energy system look if we were to aim towards a net zero emissions world? It will certainly start to look a lot more complicated. And this is, believe it or not, this is a simplified vision of how this could look in the future. But the main thing that you see here is a lot more happening in the make piece, where sources of primary energy, renewable or others, are not only converted to electricity, but also biofuels, to hydrogen, to ammonia, to synthetic fuels, and even there's capturing CO2 at the point of use, or in direct air can also play a role as well. And these ultimately serve all of the end uses. So today we're going to focus on the hydrogen, sort of the pink shaded area here. And this is what that looks like, where not only can biomass or sources of waste heat or waste energy rather, or electricity can produce hydrogen, but so can natural gas. And while we won't get into detail today about how those multiple sources for hydrogen, we're happy to do that at a later time, or what role hydrogen might play in how ammonia or synthetic fuels or how hydrogen can serve as a feedstock. We're going to focus today on how hydrogen can be an energy source for traditional gas utility customers, which is to say residential, commercial, and industrial end users. And we're going to focus broadly on the topic of blending into the pipeline gas. Now, you might be curious, okay, so for all of these diagrams and how things are oriented, how does this play out in terms of the actual emissions reduced, and what might all of this cost? While we won't cover that here, I'd invite folks to take a look at a recent study that we put out there. It's publicly available with the link there, where in partnership with the Electric Power Research Institute, we've explored modeling at an economy-wide level how these pathways might play out in different scenarios to get to net zero by 2050, and even compared them to other studies coming from university groups like Princeton and other entities as well. So an interesting way to look at some of that, but we won't cover that here today. So another way that we know that hydrogen is a piece of a puzzle is that the utility industry, many of you, I suppose, are beginning to look at it directly. And we're already looking at ways to reduce the environmental impact of utility customers by looking at renewable or low carbon hydrocarbons. Oftentimes that takes the form of biomethane or renewable natural gas, but there's also other forms of renewable LPG, biodiesel, et cetera, ways that we can reduce the impact of how traditional conventional fossil fuels are used today. And from a researcher standpoint, these are basically drop-in fuels, so we don't spend a lot of time examining what the impacts are on end users, but there's some work around trace contaminant impacts. Now, hydrogen is a bit of a different story. Now, you can see on the map here, this is a chart where the American Gas Association tracks how many states and provinces have active hydrogen blending initiatives, in many cases involving customers. And the main point there is that most parts of North America are actively looking at hydrogen as an energy decarbonization vector. And in many cases, there are multiple pilots per province or state. In some cases, these are involving up to 10,000 utility customers. So this is moving quite rapidly. And some of these field research efforts, you can see some photos here where my colleagues at GTI Energy are working with utilities that are performing these blending demonstrations, looking at how their customers might be impacted by blending hydrogen into their gas grids today. Okay, so now we're going to cover some of the basics here about hydrogen as compared to natural gas. And natural gas we'll sometimes refer to methane rather than natural gas. Generally speaking, methane is the major constituent of natural gas, up to 90 to 92%, in some cases even more. But it's the major constituent there. Hydrogen has very different properties from natural gas. Some of these properties may be familiar. You may already know that it's a smaller molecule. It has a lower volumetric density. It's more reactive. It's more readily ignited. It can have a higher flame temperature. It can be more flammable. But of course, you also might know that there is no carbon or carbon dioxide emitted when you use hydrogen, whether through a fuel cell or in a combustion process. Because hydrogen converts fully to water vapor, the exhaust of a combustion process might be more humid. You might also know that a hydrogen flame is a lot less visible. It's not invisible, but a lot less visible than a natural gas flame. These all have impacts on how these combustion processes and other processes are controlled today. And some things that we're going to talk a lot about combustion terms today. So I want to highlight how there are different flame types here. And they're organized by how much fuel and air are mixed together prior to ignition. Going from non-premixed, where there's no fuel and air mixed prior to ignition, think like a candle flame, to partially premixed. Some of the air that you need to fully combust are mixed with the fuel before it's ignited, but not all. And then fully premixed. This is a lambda value greater than 1 here. Now, we want to talk about interchangeability here, and I'll cover this chart here as well, where a lot of these important properties that we are very familiar with, things like the higher heating value, things like the Wobbe index, these change as you blend hydrogen into natural gas. And we can predict some of how these equipment and customers might be impacted based on this, but this doesn't tell us the full story. So while we will talk quite a bit about the Wobbe index and things like the combustion air requirement index, the fuel composition can tell you what might happen, but it doesn't tell the full story. The chart here on the right-hand side shows how some of these key properties change as you add hydrogen into a methane blend, substituted as natural gas. Just to use as a marker here, so some of these trends are linear, some of these trends are non-linear. So just to use 30% as a blend ratio, which you'll hear the 30% value quite a bit in today's talk. A hydrogen natural gas blend is about 26% less dense than natural gas. It has about a fifth of the reduced heating value on a higher heating value basis, but it only has about 7% reduced Wobbe index. That's going to be an important thing we'll come back to later. It requires 23% less combustion air, and overall, hydrogen requires a quarter of the combustion air to fully combust relative to natural gas. That's another important trend we'll come back to. And it also does not result in a 30% reduction in CO2 emissions, but rather a 12% reduction. And this purple line here is nonlinear because of the reduction in energy density. We need to burn more blended fuel to meet the same heating demand or same temperature target. And that means that it's not a 1-for-1 for CO2 reduction. It's 30% to 12%. So I put up this table of properties here for technical audiences. I won't go through what all of these mean here. If you're somebody who is in the combustion field, a lot of these terms are going to be familiar, but I am going to group them in terms of what the important impacts are. So for the first set of metrics here where we're comparing the impact of methane, a 30% hydrogen methane blend, and hydrogen. Things like the molecular weight, the weight of the molecule itself, the density of the fuel, the heating value, and the Wilby index. These are very important for interchangeability, but just to reiterate, the CO2 factor is nonlinear. So a 30% blend results in maybe a 12% reduction in CO2. When we're talking about the air to fuel ratio and the flame temperature, it's worth noting that the flame temperature is hotter, the fuel air to fuel ratio is lower, but these can impact each other, meaning that if the air to fuel ratio has more air than as you add hydrogen, that can cool off the flame and that can mitigate this flame temperature issue. So it's important to look at these properties together, but not in isolation. Now let's talk about things like the flammability limit, ignition energy, and detonation cell size. These are very important when you're designing for safety within the equipment and also within the facility as well. And so while methane and hydrogen have a similar lower flammability limit, there's a big difference in the upper flammability limit, meaning a small amount of air mixed with hydrogen is ignitable in a way that is not the case for methane. This is very important when thinking about purging air out of systems. We have to be more careful about that with hydrogen relative to natural gas. But also, this is advantageous when we think about designing for hydrogen, meaning that we can put a lot more air into a combustion process and still have it operate. That helps us control things like NOx for industrial applications. The last topic here points to a topic about flashback. So one thing that folks may also know is that hydrogen burns faster than natural gas. And that's really pointing to this laminar flame speed here. You can see it's up by about a factor of 6. So as we increase the flame speed, the flame wants to move closer towards where it's being injected into a process. That increase or that flashback can create an unsafe condition, and it's further made difficult by this quenching distance, meaning that the hydrogen flame can get closer to a wall and still sustain in a way that you have this sort of curvature that moves back towards. So we'll talk a lot about the topic of flashback as we go forward here. Now, some of these properties are interesting to chart here. I won't spend a whole lot of time on this, but just to drive home a few points here. And one of the main points here is that the air to fuel ratio of a combustion process really matters. Most appliances and industrial equipment out there do not directly control air to fuel ratio as the fuel changes. What does that mean? That means that if you took a cooking appliance, or if you took a boiler, a commercial boiler, and you operated it with natural gas, and then you operated it with a hydrogen blend, because of the reduced amount of air needed for hydrogen to combust, and the fact that that air will still be there, we will have what we call in the combustion field a shift leaner, meaning this value for lambda will go up. So while we might be worried about the flue gas becoming more prone to condensing, which is an increasing dew point here, we also have to think about shifting because we're moving the air to fuel ratio at the same time. The same applies for adiabatic flame temperature. While the flame temperature does go up for a constant air to fuel ratio, the air to fuel ratio is also changing. And so as it changes, we go down here, and it's possible for a flame to get cooler as we add hydrogen for this reason. It's a little complex, but the main thing is that we have to think about these properties together, not in isolation. Another thing to think about here is in terms of flame stability. Mentioned that the laminar flame speed increases for hydrogen relative to natural gas. I mainly want to point to you here as we're looking at the flame speed as a function of air to fuel ratio for different hydrogen fractions. I mainly want to point out that these lines are very close to each other until we get to about 75% or 100% hydrogen. That means that while this is a very important issue for us to pay attention to, this flashback and stability issue, it's really mainly a thing we have to worry about when we get to much, much higher blends. And this is also a factor for quenching distance as well, for the same reasons. Now, I also want to drive home the point that the type of burner matters, and there are lots of different types of burners out there. The vast majority of appliance burners are what we would call partial premix. And this probably looks a little familiar. It looks like a water heater burner or a cooktop burner where you have an orifice ejecting the natural gas under its own, the manifold pressure. Some of the air needed mixes with that natural gas, and that air to fuel mixture, which is still not enough to ignite, comes over here and it's ignited, and the rest of the air that it needs comes in from the combustion chamber here. This is very common for boilers, for water heaters, for most HVAC, most cooking. So majority of residential and commercial equipment use this kind of thing. How does hydrogen typically impact this? Well, as we are increasing, we need to think about two reaction zones here, the primary and the secondary. The primary reaction zone will shift closer to where it needs to be in terms of air to fuel ratio. And that means that we need to think about stability in this zone here, but not as much in this zone here as well. But this, we'll look a little bit later on what we see from testing, and it tends to balance out for blending ratios up to 30%. Different kind of burner is a premixed burner. This is where we are intentionally mixing fuel and air at a specific ratio, typically with a blower and some form of a mixer, and pushing that under pressure into a burner in a combustion chamber where there's something like a flame holder, usually a screen, perforated plate, metal mesh, woven fiber, even metallic foam. These can adjust their air to fuel ratio, but typically that's done through a pneumatic signal. And what that means is that we need to think about these a little bit differently. They will shift leaner as well, unless they are trying to actively control for the change in the fuel, which is less common in the US. It is quite common or more common, I should say, in Europe. And what does this apply to? This applies to high efficiency things like tankless water heaters, ultra low emission appliances, and things like that. We won't cover so much about industrial processes here, but this is an area where we're also focusing on hydrogen blended impacts. We do have a third type of burner here that we don't typically see in residential and commercial buildings. This is called a diffusion or a non-premix flame. This goes back to that candle example where the fuel and air meet at the flame itself. This is very common for atmospheric heaters, industrial furnaces, think the metals industry, for example. This is where we need to think about how adding hydrogen, while it does not change the stability as much, these tend to be very stable flames, that the flame itself will become smaller because of that shift in flame speed. And that can impact process temperature, something we need to pay attention to. This is also quite suitable for 100% hydrogen, where a little bit more care is necessary to convert a partial premix or a full premix burner to 100% hydrogen. There are partial premix burners used in industry as well. These are typically for dryers, process ovens, and even as a means of controlling emissions like NOx. We have to think just like we do about the other premix systems, so there are some similar trends there. Main point, if you take away anything from these diagrams, is that the type of burner matters in terms of how hydrogen will impact these equipment and appliances. I'll quickly go, not in the interest of time, I won't spend a lot of time on this slide here, but just say that we also need to think differently about engines, turbines, and fuel cells. While these are certainly less common than the appliances and industrial equipment that we were talking about before, maybe with the exception of backup generators, this is an area where we are actively looking at these impacts as well. So I would be happy maybe in a later conversation to dive into this topic, but just say that this is an active area of development. Okay, so when we think about our hydrogen-focused research at GTI Energy as it relates to utility customers, we kind of put it into three buckets, and our research questions depend on those buckets. The first one sort of follows from what we're going to focus on today. What happens when everything out there that's designed and certified for natural gas that the customer owns, how is that impacted by blending hydrogen, and how does the blend of hydrogen impact that? Does 10% matter more than 20%, et cetera? Another topic is, what does it mean to convert the infrastructure and the end users to be able to accommodate 100% hydrogen? I can say definitively that there are relatively few, if any, systems out there today that are designed for natural gas that would accept 100% hydrogen. The fuel is too different, it's something that you would need to retrofit for. And there is research that we have ongoing looking at that. These are both envisioning a future where hydrogen is produced centrally and either blended into the gas grid or distributed through a separate grid overall. These are both things that are moving quite fast in Europe, as I'm sure some of you are aware. The last topic is hydrogen microgrids. If you produce hydrogen and store it close to the end use, the customer should be prepared for wider swings in the hydrogen blending, as the demand shape will determine what the blend ratio could be in some scenarios. For this, we are working with, we have hydrogen microgrids that we are operating. We have end-use equipment that we are working to develop full fuel flexibility, meaning they're able, through controls and design, to operate at a 0 to 100% and cover the full range. I mentioned before that that's not something you would do with something designed for natural gas, but it is possible. But those are the three areas here. Today, we're going to focus on the first category, which is actually the biggest category of our activities with our utility partners. What are the impacts of blending into the gas grid? And I'm actually going to speed up here. What I'd like to do, the main goal is to introduce some key concepts, try to give you a sense of where the research is right now, what the key findings are, and would invite through the Q&A and maybe subsequent engagement on diving into the details. So just forgive me in advance, I am going to speed up here a little bit. So the first key concept is that the gas industry has a legacy of operating gas grids that have hydrogen-rich blends. Now, I think many folks might be aware that the Hawaii Gas operating in Oahu has about 30,000 customers that, going back to 1970, have used mainland equipment with mainland operating procedures and delivering up to a 15% hydrogen blend. In Hawaii, they gasify naphtha through a refining process, and that syngas, which is not natural gas, which has some hydrogen in it, is blended and delivered to those end users. Not a lot of issues there as far as we know, but even there are larger networks of more hydrogen-rich gases, particularly in Hong Kong and Singapore here. And the video here shows this is an appliance in Singapore that's operating on a 65% hydrogen mixture. And this town gas, these appliances are certified for this town gas. So this is something that's still happening today. However, I think as many of you probably know, if you went back to the World War II period and before, an area that we've studied, that this was common throughout the US, that even here in Chicago, we had multiple manufactured gas grids where inputs like coal, petroleum, and other fuels were gasified, and these hydrogen-rich gases with properties, some of the properties that are shown in this table, were delivered for long periods of time for lighting, heating, and industrial processes. The conversion from the manufactured gas network, which occurred from about the 1930s to the 1950s in the US and Canada, is something that we should, as an industry, return back to understand how that conversion happened. In some cases, like here in the Chicago area, there was a gradual blending process where natural gas was gradually blended into the manufactured gas grid so as to gradually convert the customers. In other parts, and later on in the 40s and 50s, in places like Washington, D.C. and New York City, the conversion was node by node, one day manufactured gas, the next day manufactured gas. Depending on how this hydrogen economy evolves, utilities may take different approaches here. Another thing I want to highlight, in addition to there being a legacy and current effort to design appliances to operate for hydrogen blends, the industry, the heating equipment industry, has really responded to this topic broadly. So today, one thing we want to highlight is that for residential, commercial, and industrial customers, that there are solutions now available, in some cases certified, to operate with a hydrogen blend or 100% hydrogen for customer distribution, for the gas train leading up to a heating appliance or heating equipment, for the controls within the boiler or other process in terms of ignition controls, flame supervision, those sorts of things, and burners themselves and equipment as well. So this is an area that's moving quite fast. I want to cover a key topic here of the interchangeability of fuels. So as we think about blending into the gas grid, we have to think about tariffs where things like the higher heating value and the Wolbe index are defined. You can see on the chart here, I'm using SoCal Gas and TC Energy, a distributor in Canada, as two examples here. You can see how, given their straight line min and max allowable tariffs, how blending hydrogen into different reference gases might impact in those areas here. And this is something we have to pay attention to because natural gas is a mixture, and how it is mixed and what Wolbe index it has can shift depending can limit how much hydrogen is blended if we use these limits. And the last thing I'll highlight too is there are burner interchangeability indices as well. And while the Wolbe index is the most common index used today to express how different customers could use different fuels that have the same Wolbe index, there are burner interchangeability indices that are used today as well. And some of these are estimate the impact on burners of flame lifting, flashback, yellow tipping, and other phenomena. These are not widely used, but just using the SoCalGas example here, they do have limits in their injection tariff for these properties here as well. So these are things that were originally developed for this conversion from the manufactured gas era, and will need to be broadly updated as some of our research is moving towards as other fuels are blended into the gas grid. So I quickly want to, and I can see that I'm going a little bit, I'm not going fast enough. Let's put it that way. I want to go into some themes from the research here. When we are testing equipment designed and certified for natural gas, what are the outcomes? What are the big themes? We've tested maybe more than 90 pieces of equipment so far for industrial and residential and commercial customers, trying to answer some very basic questions. Does it cause the equipment to malfunction? Does it lead to unsafe temperatures? Does it adversely impact the efficiency? Does it increase NOx or CO emissions, carbon monoxide emissions? Does it increase leakage within the facility? And does it reduce the heat output? And as you see here, just in terms of broad themes, not likely for all of these, except for the reduction in heat output, which is in excess of what the Wolbe index would predict. We did publish a 2024 meta-study here looking across our research and also research from other groups, like universities and other entities, 30 or more studies here to look at what are the trends in terms of the impact of flame stability and so forth. And so we're trying to work with our research partners and peers to aggregate these topics to provide information to the industry here. And while I do have, I think in the interest of time, I do have more slides that go into the detail on these topics here, but I also want to have some opening for questions and answers. And so maybe I'll keep these slides here and pull them up in the discussion and leave them here for your reference as well. I'll pause here for questions.
Thank you, Paul. This has been fantastic. And reminder, everyone, the chat and Q&A functions are both open. Please feel free to use them. We definitely welcome questions. Paul, I think my question, and maybe I misunderstood it earlier because it seems like you address it here, was regarding, I thought I heard you say there was a possibility of increased nitrogen oxide emissions, but it looks like that's not likely here. Did I misunderstand that earlier, or what led to that potential increase for an emissions?
Sure. I'm going to zip to the NOx slide here. Give me for a second while I do that.
Take your time.
Yes. Okay, so I'll try to quickly explain it with this slide here. This is a chart here that shows for a large population of boilers and water heaters tested in Europe, a large population of residential water heaters, and a large population of a whole bunch of different equipment, everything ranging from furnaces to fireplaces to cooking equipment. All of these show the NOx emissions as you increase hydrogen blending up to 60%, 90%, and 40%. And the reason that the trends tend to go down is that while you're exactly right, in principle, the NOx, a hydrogen flame is about 270 degrees Fahrenheit hotter than a methane flame. As we blend hydrogen into the natural gas for these appliances, we're not having any adjustment to the fact that it requires a quarter of the air. That air is still there and it cools off the flame, and a cooler flame has lower NOx. This is a very reliable value, or a trend, I should say, that the NOx emissions, and for basically the same reasons, the carbon monoxide emissions decline as you blend into these appliances. And believe it or not, and this chart here shows that we have more recent data on industrial furnaces where NOx emissions are also flat, whether or not you make an adjustment to stay at the same heating rate.
So I think many of us have seen studies suggesting that certain cooking or other activities can impact indoor air quality. What you're suggesting is that, well, maybe not what you're suggesting, what I'm extrapolating from what you've just said is that as hydrogen blending increases, whatever those emissions and impacts on indoor air quality may or may not be are likely to decrease, perhaps not
That's correct.
proportionally, but to a degree. Okay, great.
Yes.
And and now I'm going to ask you to go out on a limb, and maybe you're not comfortable doing that, but I want you to predict the future a little bit if you would.
Mhm.
If the systems we have today aren't ready for 100%, but we think they're in many cases ready for 30 or perhaps more, where do you see this landing in, if not the near term, in the foreseeable future? Do we get to 100%? Not on the microgrid scale, because I know you addressed that as well, but at the large scale, what do you see as the future for this?
Great question. So GTI Energy and maybe some of the attendees, you are as well. We're involved in efforts with UL, with the CSA group, to address this question from a standards point of view. But just from the research point of view here, we do view 30% as sort of an upper limit for blending natural gas, and I'll try to explain why. It's really for two reasons. The first one is that while lots of equipment have shown, you saw previous charts that I threw up there quickly, that where appliances operated up to 60%, 70%. That tends to be where we start to see stability issues being the problem. We have, and others have seen, flashback instances. These videos here show that at a 30% or a 25%, a furnace burner or a dryer burner will have a flashback condition where the flame will suck back and anchor on the orifice in an unsafe way. We've seen it with furnaces as well. This is highly intermittent, which is a fancy way of saying random, and it's yet unexplained. And this really starts to occur around the 25 to 30% range. The other reason for limiting to 30% is a little bit more fundamental, and has nothing to do with the appliances. A lot of the buildings, including some of our labs, I have some photos here of our laboratories, were designed for hazards brought on by natural gas and fuels like natural gas. So whether or not a leak of natural gas would ignite by a electrical spark from a lighting, from lighting, from a fan motor, from things like that, that most buildings that I'd imagine that utilities are serving today have this lower hazard classification. For a facility to operate, and the shift tends to be at about 30% hydrogen, to have a class 1 division A, or sorry, class 1 division 2 hazard classification from the National Electric Code, you need to have different lights, different motors, different ways to manage the electrical risk. And from our standpoint, we've addressed this issue by creating ventilated enclosures, so sort of buildings within buildings. And this is really so we can operate equipment above 30% hydrogen blended in a building that isn't otherwise set up for that hazard classification. So while the end use equipment might be able to go to operate safely above a 30% blend, the electrical code for most buildings do have this, I don't want to call it a hard limit, but do have this additional limit to consider.
That makes sense. And I'll ask one more question that I just received before we uh, perhaps let you get back to your day job. Um, what about over the next 5 to 10 years? What do you see happening in this space, and where kind of can this go in the near term?
From a technology standpoint, maybe I'll phrase it this way, or think of it this way. From a research finding standpoint, we hope that we're close to answering most of the questions that would permit natural gas utilities to blend anywhere from 5 to 25 or 30% if their regulators and the codes and standards authorities would permit that. There's a increasing body of evidence for that. I will say that that is a significant amount of hydrogen. Just as one thought experiment, we looked at how much hydrogen would be necessary to get up to a 20% volume mix in just SoCal Gas's network, so just Southern California. That amount of hydrogen to meet that ratio exceeds the total US demand of hydrogen right now overall. So that's one way of saying that the supply is going to become limiting for that as well. Where we are seeing a lot of interest and we are having a lot of activity is around industrial clusters and around hydrogen microgrids. Hydrogen is, in some cases, it's easier and it could be less costly to store as an energy carrier for a long period of time relative to batteries or other forms of energy storage. And we have projects right now involving the US Army and some other entities to explore that topic. So I think in the near term, the early adopters of hydrogen, so to speak, are going to be industrial clusters and are going to be microgrids that where the ability to be off grid for longer periods of time is a strong driver.
Fantastic. Thank you for that insight. That makes sense. Well, I really appreciate your time today, Paul. Thank you to everyone who attended. Seeing no more questions, I will happily give everybody back a few minutes for their lunch break. And Paul, again, thank you very much on behalf of NGA and everyone. Thank you for your participation.
Thank you. Appreciate the opportunity.